Hello and welcome to the Land and Climate Podcast. My name's Bertie Harrison-Brudzinski, and today I'm talking to Mark Jacobson about his new book, published yesterday by Stanford University Press, titled Still No Miracles Needed. Mark is a professor of civil and environmental engineering and the director of Stanford's Atmosphere and Energy Program. He's well known for his prolific academic output and policy engagement, promoting truly clean and renewable energy systems that minimize air pollution and avoid reliance on biomass, nuclear power, or so-called unicorn technologies, such as carbon capture and storage, nuclear fusion, or small modular reactors. In 2011, Mark co-founded the Solutions Project to advance these ideas alongside energy executive Marco Krapels, the filmmaker Josh Fox, and Hollywood star Mark Ruffalo. This provided the basis for the Green New Deal in the USA and helped steer energy policy in California and in Bernie Sanders' policy platform.
So these IAMs, they're just making these really simple, outdated assumptions. So they're just assuming that the carbon capture is actually reducing carbon from the air, when in fact, when you look at the whole system, it's actually increasing the carbon. So until they actually account for the opportunity cost emissions, they're meaningless numbers. This is complete nonsense.
I began by asking Mark to run through some of the ideas in the book. We're going to get straight into some of the details, but bear with us and we'll circle back to the bigger picture and his own journey and experiences later on.
We're looking in this book, Still No Miracles Needed, which is really a book that looks at, can we solve today's climate, air pollution, and energy security problems all at once with just clean, renewable energy? And the answer, fortunately, is yes. But we specifically look at air pollution, climate, and energy security simultaneously. A lot of people will look just at climate, which is not good because there are proposed solutions for climate that might arguably be okay for climate or not too bad, but they're definitely bad for air pollution. And another example, aside from ethanol, carbon capture, direct air capture, blue hydrogen, which is hydrogen from gas that has carbon capture, electrofuels. These are other examples that are being pushed today, are technologies that definitely worsen air pollution. And I speak of air pollution with the knowledge that about 7.5 million people die every year from air pollution, and hundreds of millions more, if not billions, are ill from air pollution every year. So this is, and the cost today of air pollution is even greater than of climate. So we have to consider air pollution simultaneously with climate if we really care about solving problems. And so if we do, then we cannot use certain technologies like biofuels, carbon capture, direct air capture, blue hydrogen, electrofuels, which continue combustion, because combustion is the problem. We do have sufficient clean renewable energy resources, and we have storage technologies, we have electric vehicles, we have electric heat pumps. We have right now 97% of all the technologies we need to solve the climate, air pollution, energy security problems the world faces. What we don't have right now, but we know how to do, is our long-distance aircraft, long-distance ships primarily, which will probably be hydrogen fuel cell electric, maybe some battery electric. Well, there'll be short distance, maybe medium distance aircraft ships will be battery electric. The long distance will probably have to be hydrogen fuel cell electric. But aside from that, we have everything we need. There is this one solution, and that's really the only solution, because things like carbon capture, direct air capture, for example, they don't reduce carbon in the air. They increase it because there are opportunity costs. It takes a huge amount of energy to extract carbon dioxide from the air with synthetic technologies, as opposed to with trees. Now, using trees to reduce carbon from the air, that's fine. It doesn't take human energy to do that, except for planting the tree. But you're not going to be able to take out a huge amount of carbon by growing lots of trees, unfortunately. You can help. But what I'm talking about is synthetic direct air capture, where we have machines and equipment to remove carbon dioxide from the air. In Iceland, there's a plant that takes CO2 out of the air, and it's about 5,000 to 6,000 kilowatt hours per ton of CO2 removed from the air. And that translates into about, I think it was like 167 to 200 grams of carbon dioxide removed per kilowatt hour of electricity and heat, because it's using both electricity and heat for the removal. But if you used a kilowatt hour of wind or solar, in this case, they're using geothermal, but let's say you use that 1 kilowatt hour of geothermal to replace a coal plant. A coal plant is emitting 900 grams of CO2 per kilowatt hour at the stack and another 400 or 500 from upstream. So it's on the order of up to 1,400 grams of CO2 per kilowatt hour. So if you're using 1 kilowatt hour of geothermal energy just to remove 167 to 200 grams of CO2 from the air, you're preventing that geothermal from getting rid of 1,400 grams of CO2 from a coal plant. Now, that means you're really increasing CO2 by a factor up to 7, maybe 8, because there is a limited amount of clean renewable energy that can be deployed on a fast time scale. And you're basically taking renewable energy that wasn't being used for anything else, and now you're preventing it from being used for something useful. And it's not only replacing electricity generation, it's Iceland, they don't have any coal actually, but they do have coal for heat and other processes. It's still a lot of CO2 that's being prevented from being reduced because that geothermal is being used for taking carbon out of the air. So there is actually no case where direct air capture, carbon capture actually reduces CO2. It only increases CO2 when you look at the larger scale. If you just look at the stack, yeah, you see a decrease. But when you look at a larger scale, the whole system only have an increase. And that's one of the fallacies that are uncovered in this book. We talk about technologies that are not needed or not useful. What is useful and needed are things that can be deployed quickly and eliminate air pollutants and greenhouse gases simultaneously and provide energy security. And those technologies we call wind, water, solar technologies. So onshore and offshore wind, solar photovoltaics on rooftops and in power plants, some concentrated solar power, geothermal, electricity, hydroelectricity primarily, and also some solar and geothermal heat are included. And the other aspect of this, so you provide all your electricity and heat from wind and water and solar, but you also electrify all energy sectors so that everything is powered by electricity and heat instead of from combustion. To electrify, if you think of the main energy sectors are electricity, transportation, buildings, and industry. Well, for transportation, we'd go to battery electric vehicles, some hydrogen fuel cell vehicles for long distance heavy transport. For industry, we go to electrifying all high temperature processes with arc furnaces, induction furnaces, resistance furnaces, dielectric heaters, electron beam heaters, or alternatively, using what are called fire bricks, which are a new technology. Fire bricks are bricks that are made of the components of dirt, like silicon, magnesium, aluminum, and chromium. And they can store heat up to 2,000 degrees Celsius for many days to weeks because they're insulated with other bricks. And they get heated with excess wind and solar because they have resistance heating elements in them. Whenever you have extra wind or solar, you heat the bricks, store that heat. When you need the heat for industry, you run air through channels in the bricks. The air gets hot. That air is then channeled to a nearby process to melt metals. After it's used there, you can use it in a second process because it's still hot to melt something else or to do some other process that requires lower temperatures. This can replace 90% of furnaces in industry, and it's really low cost because the fire bricks are made mostly of dirt. So there are these technologies in industry we can use, and then buildings. Buildings are actually very straightforward. We just get rid of gas, get rid of any wood burning. For heating air and water, we use electric heat pumps. Same with air conditioning, use the heat pumps. They just run in reverse for air conditioning. For cooking, we use electric induction cooktops. And then we have insulation. We have LED lights, energy efficient appliances. We basically get rid of combustion in buildings. And even the cars are now electric. You can charge them in the buildings. Hopefully the buildings will have solar on their roofs. And you can offset all or part of your energy use, which is really beneficial because the more solar you use from your own house, you reduce the demand for electricity on the grid. And that helps keep the grid stable. It keeps costs low for everybody else because you're preventing electricity demand from skyrocketing on the grid. So you're helping everybody with your rooftop solar. So it's a win-win situation for all these wind, water, solar technologies because they help climate. They reduce costs to everybody, their direct costs and their health and climate costs. They create jobs. They actually use less land in aggregate than fossil fuels, it'll turn out. because fossil fuels, although they're not using so much land for refineries and power plants, for example, they are using huge amounts of land for the mining, drilling, abandoning wells. In the US, for example, we have 4 million oil and gas wells, 3 million abandoned ones, and 1 million active ones. And those take up a lot of land. There are millions of miles of oil and gas pipelines. There's gas storage facilities, processing stations. You've got gas stations for delivering gasoline or diesel for fuel. When you add up all the land for the fossil fuel industry in the US, it takes up 1.16% of US land area. Growing corn for ethanol, which supplies only 4% of US transportation energy, that's another 1.24% of US land area. So we're talking 2.4% of US land is used for fossil fuels plus ethanol. Meanwhile, if we transition to 100% wind, water, solar for all energy purposes, after electrifying everything in the US, we're going to use on the order of 1% of US land. So we reduce land use by going to wind, water, solar, and electrification. We create jobs, we reduce costs, save lives, save the climate, which helps feed back to lower costs in the future for everybody. So there's no loss in doing this. The only people who lose financially are the fossil fuel industry people and people who are investing in these other non-useful technologies.
When you were starting to look at these different energy types, did you have an expectation that you might come to these conclusions? Were you surprised over the course of your career to get to this point in your own beliefs and research findings?
I got into this career because when I was a kid, like around 13 years old, I would travel to San Diego and Los Angeles to play tennis. And I just noticed the smog was so bad, I would choke on it or cough, and it would hurt my eyes, it would hurt my throat. And I could see other people were affected by it as well. And I thought, why should people live like this? And from then on, I said, okay, this is what I want to do. And my career is to solve this problem. But then soon after, I said, well, in order to solve the problem, I really have to understand it in more detail, because, it's one thing just to, okay, so that's pollution. You don't understand the pollution just by looking at it. You can see it, but you don't understand it. So that's why I thought, to be credible in trying to solve the problem, to have an impact, I have to understand it first. So I spent a lot of years trying to understand this problem, and also then the climate problem, which they're very well linked because they're the same emission sources and they have a lot of the same interactions, although one's more radiative and one's more chemical. I was fortunate to understand both problems by developing computer models, both urban scale air pollution model and combined with a weather prediction model coupled with one, and then expanded out to the global scale to build a global scale climate weather prediction air pollution model. And we merged them, all the scales in between. And so that was necessary, but around the year 2000 that I said, okay, it was after the Kyoto Protocol came up, which was an international climate agreement that had been signed by the US but not ratified. And it came up for ratification in the US. And then I started looking into what's a possible way we can implement such an agreement. And I actually dusted off some notes from a class I'd taken in 1984 at Stanford as an undergraduate, where I looked at the efficiency of an individual wind turbine as a function of just the rotor diameter, the nameplate capacity of the turbine, and the mean annual wind speed at the location. And it turned out there was this equation by this professor I'd taken a class from, Professor Gil Masters, who this really nifty equation that would give you that information for pretty much any wind turbine. It turned out to be accurate within a few percent for any wind turbine in the world. So I found this new wind turbine and applied the equation to. And from that, I was able to then estimate how many new wind turbines would be needed to satisfy the Kyoto Protocol. And it was reducing 60% of the emissions from all coal in the US. If you can eliminate 60% of coal, you could satisfy the Kyoto Protocol. So you determined the number of wind turbines. It wasn't that unreasonable. And we wrote the short paper, and it was a proposal to just do this, but it's the tiniest paper I ever wrote. It's 3/4 of one page. But it got in Science Magazine, which was a big publication. And it generated more feedback than any other paper. It said you could use this number of wind turbines to satisfy the Kyoto Protocol. And that really irked them. And so there was just all sorts of pushback. But that inspired me to work more on looking at the solution. And so then I got a graduate student to start looking at wind energy, started doing wind maps, first of the US and then the world. And so we developed actually the first wind map of the world from data alone. But that spurred just more looking primarily at wind in the first few years. But then around 2007, 2008, I started looking at other renewable energy technologies. But in the meantime, I did a study on ethanol versus gasoline. I did a study on hydrogen versus gasoline. And I was looking at the impacts of different energy technologies one at a time. But in 2008, I ended up writing a paper comparing all sorts of technology. So wind, solar, geothermal, hydro, tidal, wave, but also nuclear, carbon capture, ethanol fuel. So I was trying to compare them all in terms of, I think, 12 impact categories. So not just on climate and air pollution, but also on like water quality, different types of energy security, land use, et cetera. But without looking at costs. And from that paper, which was published in early 2009, we determined that wind, solar, geothermal, hydro, tidal, wave, for example, were the least impact technologies, whereas nuclear, coal with carbon capture, bioenergy fuels were not so good. I mean, then there was different gradations of not so good, but they weren't as good as the other ones. Not like nuclear was like in the middle, so it wasn't as bad as like coal, carbon capture even, but it was certainly not as good as renewables. That was really when we defined, first of all, wind, water, and solar, and these are the technologies we should use. And that was based on science. So it wasn't based on advocacy. It was based on looking at these different technologies in terms of 12 different impact factors and what came out on the top. I mean, you expect wind and solar to be the best technologies for being clean and best for the environment, et cetera. But then the next step was, well, is it possible to power the world with just wind, water, solar technologies? So that's when we did a paper in Scientific American looking at, can we power the whole world? And that was actually published in 2009. And the conclusion was, yes, it's technically and economically possible to power the world with 100% wind, water, solar for all energy purposes. At that time, we were looking at by 2030, and it was possible to do it by 2030, but we did say for social and political reasons, it probably wouldn't happen until later, maybe 2050. It turned out that paper turned out to be the scientific basis for what's called the Green New Deal. So the Green New Deal, which is a proposal starting in the U.S. to transition the United States to 100% renewables, that was proposed in legislation in 2018 and 19 in both the House and the Senate. Yeah, that came from this whole process of what we call 100% renewable energy movement that originated from that paper. And that 100% renewable energy movement is chronicled in this book, Still No Miracles Needed, in the last chapter. But you can see the progression of how we got from that paper to really in the US, like a whole movement. We got 19 states plus DC and Puerto Rico, plus over 100 cities, plus hundreds of companies committing to 100% renewable energy. And also internationally, there are just a lot of countries that have committed to it in different ways. And then there were Green New Deal, which started from that paper as well. There was a long progression, but it was around 2008, 2009 that critical leap came to look at a holistic solution, combining renewable technologies, not just using one, or not just using wind, not just using solar, not just using hydro or something like that, but using a combination really helps to address grid stability problems, along with storage, of course. I mean, hydro is storage, but then there's battery storage today as well, and other types of storage.
Why do you think that a lot of the integrated assessment models or other kinds of modeling and scientific work that often are the basis of policy or IPCC reports and so on might at least give people the impression of different results than your own work?
They're starting with an assumption that you can use these other technologies. Like integrated assessment models, they skip the step of understanding the problems. They're not looking at air pollution, first of all. IAM, all they're looking at is, how do you reduce greenhouse gases? And so then they just start with those technologies, like, let's say you take carbon capture, because this is what they do. They'll just assume that it works. And then they'll assume it reduces 90 to 95% of CO2 from the capture equipment, which isn't even true. I mean, in perfect conditions, yeah, that's the case. But in real, if you look at all plants in the world that do have carbon capture, the actual capture rate is anywhere from 10 to 80%. So there's no case of 90% or 95% capture. So they first make that silly assumption that's just 90 or 95% capture rate. Then there's an energy penalty, which is around the 25% of all. Like if you have a coal plant with carbon capture, you need 25% more coal to run that plant. So they ignore that energy penalty for the most part. They don't actually look at mining more coal and see, what's the additional energy from mining that coal? What's the additional carbon and pollution from doing that? In some cases, they'll assume an energy penalty, but they just don't actually translate it into additional emissions. There's only one coal plant in the US that had carbon capture added to it. And what they did is they didn't add more coal. They didn't use more coal, but they built a gas plant just to run the carbon capture equipment for the coal plant. So they had to mine more gas, there are more leaks and emissions from that. And they don't consider any of this. They might assume they'll use renewable energy. But then you have to build more renewable energy because that renewable energy they were using is now no longer available to replace another coal plant. So they're not even looking at these trade-offs of the opportunity costs and that what we call the opportunity cost emissions that occur because now you can't use that renewable energy for another plant. You don't have the infinite amount of money available just to do that. So these IAMs, they're just making these really simple, outdated assumptions. So they're just assuming that the carbon capture is actually reducing carbon from the air, when in fact, when you look at the whole system, it's actually increasing the carbon. So until they actually account for the opportunity cost emissions, they're meaningless numbers. It's just complete nonsense. And the assumption, like with nuclear, is they assume, well, you can just build a plant tomorrow. But in reality, there's no plant in the world that's ever been built from a planning to operation time of less than 10 years. And today it's 12 years, even in China. And worldwide, it's up to 23 years. So North America and Europe, it's 17 to 23 years. You can't even build a plant in North America, Europe, less than 17 years from plan to operation today. So today is now, it's almost 2026. We're talking 2043 would be the first plant. Yet they assume these plants are up and running in 2027 or something like that. They ignore the cost. They ignore the emissions associated with refining uranium. They ignore the emissions associated with the background grid while waiting for the plant to be built. So by assuming that plant is built today, they ignore all the emissions for the next 17 years of coal and gas from the grid due to the fact that you can't build the plant. So you have all these ridiculous assumptions going into these IAMs that render all their results nonsense. So I would not put any credibility to anything an IAM says. It's just not feasible. So you don't even need a model to just know that these assumptions are wrong. What you do know, though, is that wind and solar and geothermal, first of all, there aren't going to be excess emissions associated with them. They're addressing both climate and air pollution. Whereas even carbon capture, it doesn't even try to address air pollution. Just because you can capture carbon dioxide, you don't capture any other pollutant coming in from a stack. In fact, because you need more energy, if you're using more coal or gas to get that energy, you're increasing pollution. The IAMs, again, are just not even concerned with air pollution. So it's key that we focus on what works and start recognizing that there's these other technologies are useless. They do not help one bit. And even if they help incrementally, we need to solve 80% of the problem within 5 years and 100% within 10 years. So we need to deploy technologies as fast as possible. There's some good news. There are examples of really fast deployments that are going on. 7 countries in the world are transitioning so fast, they can be 100% wind, water, solar across all energy sectors by 2048. And China, in fact, is building so much renewable electricity, they will eliminate all their coal and gas emissions by 2051. They will be electric across all energy sectors by then, if they keep building their electricity generators as fast as they are this year and last year. And just to put that in perspective, this year alone, they'll build more nameplate capacity of renewables, that's wind, solar, and hydro, than all the nuclear reactors ever built in history combined. So their growth rate is 20 times that of the fastest nuclear growth rate, which was in France in, I think, 1982. So there's blowing away the field in terms of the renewable installations. The amount of power they're producing at the end of this year, by the way, is equivalent to 54% of what the United States needs in 2050 to be 100% renewable across all energy sectors. So the argument disappears that you can't build something out this fast, renewables, because China is actually 54% of what US needs in 2050 to be 100% renewables across all energy sectors is already installed in China. And China emits 35% of all the greenhouse gases in the world and uses about 35% of all the energy in the world. So to have a country that big and that emits so much, transitioning so fast is a good sign. Meanwhile, US and India are on track to be 100% renewables across all energy sectors only by after the year 2130. We're still building in the US and in India, but in the rest of the world, but except for a handful of countries, most places are just not building at that speed that we need.
Just picking you up on focusing on what works, the flip side to you saying that some of the policy and popular narratives that people might know, presuming that some technologies do work better than they may actually work, is also that these same narratives and policy documents and popular science often suggest that there are these kind of hard to abate sectors or residual emissions from industries that haven't yet got the ability to decarbonize. And that's something that you dispute in your book as well, looking at things like cement and steel and chemicals manufacturing. Do you think that the kind of technological readiness of those is underestimated? And if so, why?
Yeah, in industry, some people claim that we still need to use fossil fuels or we need to use carbon capture for some industrial processes, but that's just an effort to keep those fossil fuel and carbon capture people in business. And the carbon capture people are really the fossil fuel people, because if you can sell carbon capture, then you can sell fossil fuels, because that just allows fossil fuels to continue. So there's ways to get rid of carbon emissions in cement. We first electrify all heating. That's pretty straightforward. And that gets rid of all the emissions associated with electricity and heat. But then there's some emissions from industry that are called process emissions that are from chemical reactions. So, for example, when you have calcium carbonate with cement, then you want to use the calcium in the cement, but the carbonate part off gases as CO2, carbon dioxide. And you can get rid of that because right now calcite is used as a mixture in cement, but if you use basalt instead of calcite, basalt also has calcium, but it has no carbonate. So you can develop the exact same Portland cement, ordinary Portland cement, with the calcium, but have no chemical emissions of CO2. So there are a couple of companies that are doing this. The one is called Brimstone and the other is Secrete. There's also what's called geopolymer cement, which you can also eliminate almost all the emissions of chemical emissions of CO2. So there are alternatives to that. For steel, you get CO2 emissions by using coal to purify iron ore to iron, and the oxygen from the iron ore bonds with the carbon in the coal to give you CO2. And so that takes away the oxygen from the iron ore to give you pure iron, but you release CO2 gas. And you can solve that by using hydrogen instead of coal. So you can bond oxygen with the hydrogen, and you'll get no carbon dioxide emissions, and you're also purifying the iron. So if you produce the hydrogen from wind electricity or solar electricity, that's called electrolysis, then you can eliminate those off-gassing or CO2 emissions as well. So there are clever solutions in industrial processes to get rid of chemical emissions. It's not really hard to abate. It's just people don't want to abate it because they want to keep the fossil fuels going. So they want to use carbon capture to maintain fossil fuels or to prevent a real clean solution. Imagine using carbon capture to capture the CO2 from cement. That actually not only increases air pollution, but it increases the CO2 itself. It doesn't decrease CO2. And here's the why. Because carbon capture equipment requires energy to run, and it requires equipment, and it requires pipelines to pipe the CO2 somewhere. So that energy, where is it going to come from? In the best case, it comes from wind or solar. But again, if you use wind or solar for running carbon capture for cement, you're preventing that wind or solar from replacing a coal plant somewhere. So you're actually then increasing CO2 in the air while increasing air pollution from the coal plant, which you would have otherwise eliminated. And now you have to have a bunch of pipelines everywhere. You have to invade people's land to bury pipelines. And those pipelines, what are they going to do? Well, most pipelines of CO2, 82% of all carbon captured today is used for what's called enhanced oil recovery. And during that process, CO2 binds with oil to make it less dense so it can float to the surface faster and you can get more oil out. But during that process, 50 to 120% of the CO2 that was captured goes right back to the air, because 30 to 40% of the CO2 gets released just due to the binding with the oil and the process of bringing it there and some of the chemical reactions that occur. And then another 20 to 80% of the CO2 is released due to the excess oil that you produce that's burned. beyond what you would have produced before. So 82% of all the carbon dioxide captured today just goes right back to the air due to enhanced oil recovery. So it's not even being stored under the ground. The whole thing is just a scheme. It's really ridiculous. And I just hope people can see really what's going on. That carbon capture scam is just designed to keep fossil fuels in business.
My thanks to Mark for coming on the show and to Vasco Kostovsky for our audio engineering. We will include a link to the book in the podcast blurb for this episode, along with other links to further reading. Do remember to check out the many other articles and podcasts on our website at landclimate.org. We've published 2 new investigations in the past month, one about biomass power in the USA, and another about sanctioned energy companies suing Ukraine, so do take a look at those. Please also leave a review and follow us on your favourite podcast platform if you've enjoyed this episode, and we'll be back in 2 weeks' time with another one. Until then, thank you for listening.